Well, good morning, folks. And today we want to get into a little bit about the history of the atom. This is really one of my favorite topics is the history of the atom because there is so much cool stuff that happened relatively recently. The 20th century physics was the greatest time in scientific discovery since Newton, and it all had to do with what was happening, what was being learned about the atom. But before we can get to the 20th century, we really need to start with kind of the father of the atom, and that is this guy named Democritus of Abdera. And where is Abdera? I think that's in Thrace, which was a part of Greece, yes? And it was back here in 430 BC. This is when Greece was power and intellectual power, not like it is today, going bankrupt. This is when the Greeks actually worked and thought. No offense to all Greeks, of course, but let's face it, with the euro and things, Greece is in a bit of a problem right now. So, what is it that Democritus did that made us think of him noteworthy, right? Well, he is the first with one of his buddies to propose that all things are composed of atoms. So he said, hey, everything is composed of atoms. And he said, hey, these atoms are indivisible, divisible, divisible, and indestructible. Yes, indivisible and indestructible. Good. Oops, I think I misspelled divisible. Good. Indivisible and indestructible. Well, was he right on that? Can atoms be divided? Yes, they can. So he's kind of wrong there. And are they indestructible? Well, I guess I'd give him. I don't know. That one's a tough one to really define. Indestructible. Can you turn atoms into energy? Can you turn their mass into energy? Yes. That was proven with our atomic bombs, right? So I'm not sure if he was correct in his ideas, but for a guy back in 430 BC to come up with these ideas that all things are composed of atoms, that's a pretty great accomplishment. Now, there's really not much that happens regarding the atom until we get to J.J. Thomson again. I mean, we learn some things. We're starting to learn some things about electromagnetic radiation. Thomas Young does some cool stuff, but we really don't get into much more about the atom until J.J. Thomson. And you guys know about Thomson, right? He did the cathode ray tube, cathode ray experiment, right? Experiment. And he had this ray, this cathode ray, and he hooked up some electrodes to it, and he was able to shoot a beam of particles. And then he subjected that beam to a magnetic force, and he found that the beam would bend, and it bent greater than he expected for a proton. And so he said, okay, first of all, these particles, this must be made of particles, and these particles must be negative since they're attracted to the positive side. And second, since the bend was so great, they must be much lighter. They must be much lighter than the hydrogen atom, which was the lightest atom known at the time. And so he said, hey, this must be a subatomic particle. And he said a subatomic particle, which is a negative charge, and eventually they called that the electron, right? But that's not really why we're talking about Thomson, because we want to talk about his atom, right? And what was Thomson's atom? Thomson said, hey, I think the atom is like plum pudding. Plum pudding. Well, that's an English thing. I don't know what plum pudding is. Uh, and so I kind of think of it more like, I call it the watermelon model. The watermelon model, which is kind of like plum pudding, and you'll see in a second why I say that. Let's extend the page. What do we mean by the watermelon model? Well, Thomson said the atom was a big blob of positive charge. So all this red would be positive charge. And in the middle were raisins. Well, not really raisins, electrons. And so that's kind of like plum pudding. Plum pudding was this big blob with raisins stuck in the middle of it. And that's why I think of it like the watermelon model, right? It's kind of like this is the flesh of your watermelon, and these are the seeds of your watermelon, right? And so these are negative electrons. This was just a big blob of positive charge. Positive blob. Good. And so that is what he proposed. Now, Thomson did this where he was uh, working at the Cavendish lab in England. And by the way, Thomson was born where? Thomson was born in England. He's an English guy born in 1897. He worked in the Cavendish lab, came up with this idea, and he won the Nobel Prize in 1906. 1906. Good. And one other thing we want to keep an eye on as we discuss this is, how old were these guys when they came up with their great ideas? Well, Thomson was 41 years old when he comes up with this plum pudding model of the atom. Okay? Good. Now, one of the guys who worked for Thomson is a guy named, oops, sorry, getting ahead of myself. Now we want to jump back a little away from the atom, and we need a little bit of background because these guys are going to help us understand some things a little later. And here's a guy named Max Planck. Max Planck, how do you like this hair, man? Woo, boy. I wish I had hair like that. Instead, now my hair looks like that. But well, both of these guys are Max Planck. This is before he had students. This is when he was a student. And this is when he was a teacher. And you can see what effect students have on teachers. Oh my gosh. Just 2 years ago, I looked like this. That's me 2 years ago. But what did Planck do? And Max Planck did what? He was studying a thing that I thought would always be really cool to study, and that is hot bodies. Yeah, he was studying hot bodies. Now, I'm not talking about Heidi Klum or any of these others. I'm talking about, really, they were called black bodies, and it would be like a black piece of metal, right? And you put it in a fire. Here's a fire. And when you put it in a fire, what would happen? Well, it would start to glow, and it would tend to glow different colors based upon its temperature. And so it was radiating energy. And so Planck was studying this, and he couldn't understand why it was radiating energy the way it was. According to the science at the time, this energy should all end up being ultraviolet, and ultraviolet then would fry the universe, fry the Earth, and so there should be something known as the ultraviolet catastrophe. And we know that doesn't happen. So obviously the idea that the way energy was released from a hot body was wrong. And at that time, the idea was that the energy is released continuously in waves. That energy was released continuously from these hot bodies. So Planck then said, hey, this must be wrong. We can't be releasing energy continuously from hot bodies. And he proposed the idea that energy is released in chunks. Chunks. How about no C? How about chunks? And he called these chunks quanta. That energy was released in quanta. Good. Now, he wasn't real happy with this. He really didn't believe that this was reality, but it matched the data. And he does this when he is 42 years old, and he wins the Nobel Prize. And he wins the Nobel Prize in 1918. And just kind of a side thing, you look at the name Max Planck, and so you say, okay, where's he born? Hey, he was born in Germany. And then you wonder, okay, 1918, Germany, and then 1930s, we get to Hitler and things. And what kind of guy was this? Was Planck maybe a Nazi working to help them out? Now, it's too early in 1918, right? This is World War I. But he was around and a very prominent German in the 40s and 50s as well. And it turns out that his son was actually executed by Hitler. But the guy with the funny little mustache, the evil guy, right? He executed him because Planck's son was part of Operation Falkeri. Falkeri, because he tried to assassinate Hitler in 19. Well, this is 1944 when his son was executed by Hitler. But Planck's son, tried to blow up Hitler to prevent the war from going farther. Good. Moving on. So just a little bit. That tells us a little bit about Planck. So what's Planck's big contribution? It's that energy is released in chunks called quanta. Good. And then we go to one of our fun guys, and that is Ernest Rutherford. We know about Rutherford, right? Rutherford is from New Zealand. New Zealand, right? And we know at one time he worked at McGill University in Canada. So he's almost an American there for a while. He worked at McGill and he studied alpha particles. And then after becoming kind of famous, well, really famous for studying his alpha particles, he goes and he works at the Cavendish. And who else is at the Cavendish? How about Cavendish? Cavendish, there we go. He works at the Cavendish with J.J. Thomson. Thomson was his mentor. And this is where then that Rutherford does his famous gold foil experiment, right? Gold foil experiment. The famous gold foil experiment, right? And what does he do? He takes a block of metal and he puts an alpha source in it, and he has a hole there so that the alpha particles can come out, and then he has a foil of gold, right? And now remember, what is our thinking about the atom at this time? Well, we're still working with the plum pudding model, right? We're saying, okay, there should be a big blob of positive charge, and there are points of negative charge in it, right? And so we're working with Thomson's model. And so what does Rutherford expect? He expects that his alpha particles, which he knows that the alpha particles are helium nuclei, and he expects them to just fly through because these guys are trucks. These are huge. Alpha particles are big compared to the nucleus. And so he expects these alpha particles just to fly through the nucleus without any problem. And what did he find that happened? Yeah, most of them did do that, right? Most of them flew through and there were no problems, but all of a sudden he started getting some that would fly off. Oops, that's the wrong side, sorry. Fly off at angles. And then he got some actually that started bouncing back. And that was a problem. Because how could this big blob of positive charge and negative electrons push back something as massive and as positive as a helium nucleus? And that's when he says, hey, this model here must be wrong. And what does he propose? He says, listen, an atom is made up of a massive nucleus, and in that nucleus you have all your protons. At that time he doesn't know they're protons and neutrons, but he says he has a massive nucleus. Let me get this right. A massive nucleus, and it has all the positive charge, and then somewhere out here in space around the atom are the electrons. And most of the atom is made up of what? Most of this stuff in here is empty space. Right? So then that would explain why his alpha particles, here's an alpha particle, could fly right through with no problem most of the time, but every once in a while they'd hit the nucleus, and what would happen? It would bounce straight back. And this really shocked Rutherford. He said, this is like shooting a 15-inch cell at a piece of tissue paper and having the tissue paper having the shell rebound. Now, what's a 15-inch shell? Well, think about this. It's like this is the Queen Elizabeth ship, and on that ship you have a gun, and on that gun you have a big old uh, nozzle barrel, and this barrel is 15 inches in diameter, so it's 15 inches from here to here, and you shoot out that shell, and it's flying, and here's Rutherford over here, and he's holding out a piece of tissue paper, and it would hit there and bounce back. That is not that that really happened, but he said that's how shocked he was. He could not believe that the metal foil, the gold foil, could throw back an alpha particle. And so it was completely shocking to him, and that's how he came up with his, what do we call this? We call this the nuclear atom, right? The nuclear atom. That is Rutherford's great contribution, and he does this at the age of 40. He's 40 years old, and then he wins, well, he didn't win the Nobel Prize for this, but he did win the Nobel Prize in 1908. Yeah, and which kind of brings just another interesting story. He won the Nobel Prize in 1908, but yet he did his gold foil experiment and figured out the nucleus in 1911. So why did he win the Nobel Prize in 1908? Well, this is because he won the Nobel Prize for figuring out that alpha particles are really helium nuclei, and he did that while he was at McGill University. Okay? Good. Let's see. How are we doing on time? I think that's probably a good place to stop on this episode. Next time, we're going to pick it up with one of my favorite guys. You might find him a little boring. His name is Niels Bohr. You get it? Get it? Boring Niels Bohr. Ha ha ha. See ya.